Welcome back to Module 5. Module 5 overviews and discusses the rigid pavement transfer functions and how they are used to design rigid pavements using the PMED design software. This session, or Module 5.2.2, focuses on the Crcp Smoothness degradation. This submodule is 5.2.2 and focuses on Crcp Smoothness degradation. The same type of information is included for Crcp Smoothness degradation, as was discussed for jointed plain concrete pavement smoothness degradation. As such, we will quickly review the same type of information that was already presented for jointed plain concrete pavements on smoothness degradation. There are 3 learning outcomes of Module 5-2-2 on Crcp smoothness. First, we want to explain and define the design premise for smoothness degradation of Crcp. Secondly, we want to define the Crcp smoothness degradation predicted in the PMED software. And finally, the third is to describe the regression equation for Crcp smoothness degradation. Starting with the definition and measurement of Crcp smoothness. As was defined for jointed plain concrete pavements relative to smoothness, Crcp smoothness is defined as the variation of surface elevations within the wheel path that induce vibrations in vehicles. Smoothness is quantified by the International Roughness Index, or IRI. IRI is simply the sum of cumulative movements in one direction between an axle and vehicle body of a standardized vehicle. IRI is a mathematical index of the longitudinal profile of a roadway expressed in meters per kilometer or inches per mile. IRI has been adopted as a standard measure of smoothness by the FHWA and many state highway agencies. IRI is used to quantify smoothness in the PMED design software. Smoothness in the PMED design software is used to predict Crcp functional performance, or the performance of a highway from a highway user's perspective. Smoothness is measured in accordance with AASHTO R43M or R4307, which is the standard practice for quantifying roughness of pavements. It can also be measured using ASTM E1926, which is the standard practice for computing the International Roughness Index of roads from longitudinal profile measurements. The IRI is computed using profile measurements from devices such as the inertial profiler, the dipstick, as well as rod and level surveys. The devices commonly used to measure smoothness include the high-speed inertial profilers and the lightweight low-speed inertial profilers. Next of this session is to overview the distress mechanism, or the design premise approach used to determine the deterioration or degradation of smoothness after initial construction. The design premise is the same as for jointed plain concrete pavements. The difference is that the distresses are different between Crcp and JPCP. Smoothness degradation, or the increase in variability in the pavement profile point by point in the wheel path over time, is not predicted using mechanistic empirical concepts. The approach used or applied in the MEPDG is to develop a statistical model or regression equation to determine the change in IRI from field data, which include key factors such as the initial IRI, the increase or change in structural distress over time, and the site factors to account for subgrade differential movements, climate fluctuations, aging, and surface degradation, as well as other surface defect issues. The smoothness generalized model, or the regression equation, is included on this slide. The IRI predicted over time is based on the initial IRI measured after construction. The structural distresses predicted over time, a site factor related to the subgrade site properties and climate, and then the regression coefficients or constants for the predicted variables. So the generalized smoothness model for basically all pavement types in concept is the same for all pavement types. Next is to present and discuss the regression equation for calculating IRI throughout the design period based on that design premise, but focused on CRCP. For CRCP, the only distress included in the regression equation for calculating IRI over time is a number of punch-outs per mile. The IRI predicted for a CRCP throughout the design period is based on the initial IRI at the time of construction, the number of punch-outs per mile determined in accordance with the software, and the site factor. The C1 calibration coefficients for the punch-outs term is 3.17, and the C2 calibration coefficient for the site factor is 28.35. The values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on more recent calibration results. The coefficients and exponents of the transfer function or regression equation, in other words, C1 and C2, are included in the output report for the Pavement ME design software. The site factor variable for the CRCP smoothness degradation regression equation is included on this slide. The site factor equation is the same for jointed plain concrete pavements and continuously reinforced concrete pavements. The independent variables of the site factor include age, freezing index, and percent passing the number 200 sieve. Age is the time since construction in years. This includes the cycles of temperature and moisture changes. The freezing index is the annual number of air freeze-thaw cycles. Increased freeze-thaw cycles result in increased IRI due to increased potential for crack spalling. In addition, deeper frost penetration results in increased IRI due to increased frost heave potential. Percent passing the 200 sieve is the percent passing the 200 sieves, which results in an increased subgrade volume change over time, or can result in increase in volume change over time. This slide summarizes the coefficients that were used or resulting from the regression equation for predicting IRI throughout the design period. These calibrations and coefficients include, which were defined on the previous slide, C1 for the number of punch-outs, which is 3.15, C2 for the site factor is 28.35. As noted previously, the values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on any recent results of the global calibration process. The coefficients and exponents of the regression equation are also included in the output report for the PMED design software. Reliability was discussed in detail in Module 3 and how it is applied in the PMED design software. The standard deviation of the residuals for IRI are displayed on this slide. The standard deviations of residuals is used to determine the reliability of the IRI that is predicted for CRCP. This section is a summary of the materials presented under Section 5-2-2 for smoothness or for CRCP smoothness degradation. The three learning outcomes from Module 5.2.2 on CRCP smoothness degradation included: the first, we explained and defined the design premise for smoothness degradation of CRCP, which is the same design premise for all types of pavements. The second, define the CRCP smoothness degradation included in the PMED design software. And then the third, describe the regression equation for smoothness degradation. This ends Module 5.2.2 on CRCP smoothness degradation. The next submodule of the training course sequencing is Module 5-2-3 on CRCP interpretation and adjustment of the design features and factors for achieving an acceptable CRCP design strategy.